Assalamualaikum friends, this is Mohammad Inam, and in this video we are going to talk about convergence of differential equations, ordinary differential equation into integral equations. So the contents of the video are: initial value problem will convert into the Volterra integral equation of second kind, and the general procedure and example about it. The second part of the content is boundary value problem will convert into a Fredholm integral equation of the second kind. Here we have just example. So let's see. Is a general second order non-homogeneous with variable coefficient differential equation with initial condition, that is y of a at x equals to a, it is y naught, at y prime of a is equals to y naught prime, and we want to transform it into integral equation. So for transforming this into integral equation, we need to integrate this part from 0 to 8 x. So we are integrating this from 0 to x. So let's write it 0 to x. Why I'm changing the notation of replacing x with t, because we are integrating here. So the derivative with respect to t will denoted by dot, plus integration 0 to x a of t y dot of t dt, plus integration 0 to x b of t y of t dt equals to integration 0 to x c of x c of t dt. So now here one result, that integration from a to b, the derivative of function with respect to this is just y of x at a to b will be y of b minus y of a. So we know this result. I'm using this here. This will be like y dot of t at we are integrating from a to x, sorry. So let me change them. Here we are integrating from a to x. So from here a to x, let me remove this one, plus now for evaluating this integral I am using integration by parts. So let's say this is u and this is v. It will be like a of t y of t from a to x minus a to x a dot of t y of t dt. This integral will be like this one. This will be same, plus a to x b of t y of t dt is equals to integration from a to x c of t dt. This can be written as y prime of x minus y prime of a, and now we know that from initial condition y prime of a is y naught prime. So rewriting it, y naught prime, and we can emerge this two integral as a single integral. How? This will be like a to x minus a dot of t plus b of t y of t dt. We have emerged this two integral as this one, and we can also simplify it. This will be a of x y of x minus a of a y of a. At y of a is y naught, so this will be changed into y naught. The whole part will be remaining same. So now we have y prime of x minus y naught prime plus this part plus this integration part, and last equals this part. a of x c of t dt. Now we need to integrate this equation one more time, so we will have some results. If I am integrating this one more time, this will be y dot of t from a to x dt minus integration a to x y naught prime. Keep in mind y naught prime and y naught are constants, dt plus integration from a to x a of x a of t y of t dt minus integration a to x a of a y naught dt plus, here I am writing it, a to x, the previous integral a to x, and this will be b of t minus a dot of t y of t dt square. Now dt square is equals to this part, again integral a to x c of t dt. Now guys, we need to evaluate these all integrals. So for this part it is easy, we can say that y of t at a to x minus, this is constant, we know that, so this will be outside y naught prime t at a to x. This is not constant, this is constant, so we can rewrite this one as a of a outside y naught at y naught of a to x. For evaluating this integral, we have a result that is called multiple integrals converting to single integral. The statement of result is a to x a to t n minus 1 up to so on a to t1 y of t dt equals to integration from a to x minus t n minus 1 over n minus 1 whole factorial y of t dt. This is the result, and we have already uploaded a video about it, so you can watch it. The description, the link is given below in description. So I am using this result here and here. Then this integral will be b of t minus a dot of t a to x and x minus t y of t dt, and this is plus this one a of t y t dt. The last is equals to from a to x minus t c of t dt. I have put all the terms here. Now we just need to simplify it, and we have done. So I am doing this upper part. Okay, this is okay. Y of this will be y of x minus y of a is y naught, and this will be minus y naught prime x minus a, and this will again same minus a of a y naught at x minus a, plus we can emerge these two integrals, so this will be plus integration from a to x b of t minus a dot of t x minus t, and this one plus a of t y of t dt, and the final one is equals to a to x x minus t y of t dt. Now let me further more simplifying it. We can say that this one as y of x is equals to f of x plus integration a to x k x comma t dt. This is called the general Volterra integral equation of second kind. So I can rewrite this above equation in this form. How? Let's say this is y of x. Okay, done. F of x. This is, let me introduce f of x first. F of x equals to a to x x minus t y of t dt. This part plus y naught, this part plus y naught prime x minus a, and this part plus a of a y naught x minus a. So this is our f of x. Now what is kernel? Kx comma t is called kernel of integral equation. So kernel of integral equation is this one, b of t minus a dot of t times x minus t plus a of t. This is our kernel and this is our f of x. When we shift it the other side, this will be minus and this will be minus and this will be plus. Oh yes. So we have done. This is known as our Volterra integral equation of second kind. This was the general procedure. Let's see an example of initial value problem with these two initial conditions, and we want to transform it into integral equation. We can use directly formula to transform it, or we can apply the same procedure. Here I am applying the same procedure for your understanding. So first we need to integrate from 0 to x, because here a is 0, so we need to integrate it from 0 to x. Directly integrating from 0 to x, y double dot of t dt plus integrating from 0 to x, this will be t y dot of t dt plus lambda, here lambda is constant, taking outside lambda from 0 to x y of t dt equals to 1 0 to x dt. So we know that this will be y dot of t from 0 to x, and here we need to use integration by parts. So this will be t y of t from 0 to x minus 0 to x t square, oh sorry, this will be y of t, just y of t dt plus lambda 0 to x y of t dt equals to, this will be t from 0 to x, or the simplification will give us y prime of x minus y prime of 0 plus here 8x, this will be x y of x, at 0 this will be 0, minus we can emerge these two terms as plus lambda minus 1 integration 0 to x y of t dt equals to, this will be just x. Now we need to change this y prime of 0. At x equals to 0, y prime is minus 1, so minus minus will be plus, this is plus 1. All terms are fine. Again integrating it from 0 to x, this will be 0 to x y dot of t dt plus 0 to x 1 dt plus 0 to x t y of t dt plus lambda minus 1 outside because constant, double integration from 0 to x y of t dt is equals to 0 to x t dt. So this will be y of t at 0 to x, and this will just x, and this will be same 0 to x t y of t dt plus lambda minus 1, and double integration, I am converting this double integration into single, then this is 0 to x x minus t y of t dt is equals to, this will be x square upon 2. So now here it is fine. Let me simplify it more. This will be just y of x minus y of 0. We know that y of 0 is 1, so this is minus 1 plus x plus, now this 2 integration can be merged to 1. This will be 0 to x t plus lambda minus 1 x minus t y of t dt. The last term is equals to x square upon 2. Or we can shift these two terms here, plus 1 minus x, and removing from here. So this is our required Volterra integral equation of the second coin. Friends, we have the same problem, but now this is boundary value problem because initial conditions are changed. Let me transform this boundary value problem into the Fredholm integral equation. The procedure is same, but just there is a simple change in the procedure, and otherwise all procedure are same. So first we need to integrate again from 0 to x. This will be y dot of t from a to 0 to x plus this will be t y of t from 0 to x minus integration 0 to x y of t dt plus lambda 0 to x y of t dt equals to just integration of 1 from 0 to x with respect to t is just x. So let me simplify it further. This will be x y of x minus, we can simplify this to integral as lambda minus 1, and this part is removed. This is the simplification. Now y dot of t at x, just y prime of x minus y prime at 0 plus x y of x plus lambda minus 1 from 0 to x y of t dt equals to x. Now we don't have initial condition, so we don't know about this term. So let's say this is a constant, any constant is named as c. So I am removing here c. Now again integrating from 0 to x, this will be y of t from 0 to x, this will be minus c x, this is minus cx plus integration of from 0 to x t y of t dt plus lambda minus 1 is constant outside, double integration 0 to x y of t dt equals to, this term will be x square upon 2. Now simplifying it, this will be y of x minus y of 0. Y of 0 is 0, so let's say just 0 minus cx plus, these two terms can be reduced into 1, 0 to x t plus lambda minus 1 x minus t y of t dt is equals to x square upon 2. we have applied the same procedure, only the difference is just this C. For eliminating this C, we need to apply this second condition, that is y of 1 equals to 0. So let me apply that condition. At x equals to 1, y of 1 is 0 minus C plus 0 to 1 t plus lambda minus 1 minus t y of t dt equals to 1/2, or C will be just minus 1/2 here and plus C here. So we have the value of C now. Now we need to plug this value of C in here. So we will have y of x minus C. This minus minus just plus x by 2, and this minus plus minus 0 to x t plus lambda minus 1 minus t y of t dt. Okay, so this is fine. Now this term 0 to x t plus lambda minus 1 x minus t y of t dt is equals to x square upon 2. Okay, so now we can break this. This is 0 to 1. Sorry, this was 0 to 1. Now we can break this our interval of 0 to 1 in two parts. How? Let's see. Y of x equal plus x by 2 minus 0 to x t plus lambda minus 1 minus t y of t dt plus x to 1. We have break this interval from 0 to 1 in two parts. First is 0 to x, then second is x to 1. So this is x t plus lambda minus 1 minus t y of t dt. Okay, now that term 0 to x t plus lambda minus 1 x minus t y of t dt equals to x square upon 2. Now we have two integrals with same range, so we can merge them and this will be separate. So the final will be y of x. This part is no more here. I can rewrite this one from there. And this is from positive plus 0 to x t plus lambda minus 1 x minus t, and this will be minus x t plus lambda minus 1 minus t y of t dt. So we have merged these two integrals as one. Then this one from x to 1 x t plus lambda minus 1 minus t y of t dt is equals to x square upon 2 minus x by 2. We have done. Now we can define our kernel of integration in two parts. Let's see how. We can say that our kernel of integration is equals to, from 0 to x, this is this one, t plus lambda minus 1 x minus t minus x t plus lambda minus 1 minus t. This is our integral kernel when our range is from 0 less than or equal to t less than or equal to x. Whenever t from this range, we use this kernel, and if x t plus lambda minus 1 minus t, if our t, if we use this range then this is fine. We can define our kernel in two parts, and this will be like y of x plus integration from 0 to x kernel y of t dt equals to x square upon 2 minus x by 2. Here integration is 0 to 1. This is so called Fredholm integral equation of second kind. So we have done convert our differential equation into boundary value problem into integral equation. This is the result. Just the difference of procedure is we need to eliminate c, means the value of y prime of a. We need to just eliminate the value of y prime of a, and all the things are same. If you like the video then thank you guys for watching this video, and don't forget to subscribe.